Mixtures of gases. So kinetic molecular theory says that the gas particles bump into each other, they don't interact, and there's lots of empty space. This predicts that the components of a gas mixture, if you have two different gases in a container, that each of those gases is going to act independently of the others. They don't interact with each other. There's all this space, so they act like they're the only thing in there. The pressure, then, from any component of the gas mixture is called a partial pressure. So if you've got two gases, gas A and gas B, gas A is bouncing off the walls, creating a pressure. Gas B is also bouncing off the walls, creating a pressure. So the total pressure of that mixture is the sum of the individual pressures. Those individual pressures are called partial pressures because they're part of the overall pressure. The partial pressure is equal to the fractional composition times the total pressure. If gas A makes up half of the molecules, then its pressure should be half of the total pressure. If gas A is 90% of the total amount of gas, then its pressure should be 90% of the total pressure. Does that make sense? Kind of? The air in our atmosphere is a mixture of gases. It's 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and then other gases in much smaller amounts. So the nitrogen, which is most of the air, exerts a certain pressure. It's 78% of the total pressure. What's the pressure of the gas in the air in this room? It's a good guess. Express it in atmospheres. 1 atmosphere, yeah. We're just a little above sea level. It fluctuates a little bit. It's about 1 atmosphere. 78% of that is due to nitrogen. 21% of it is due to oxygen. So here's the optimist. I forgot this was in here. The optimist says the glass is half full. The pessimist says the glass is half empty. The chemist says the glass contains 50% water, 39% nitrogen, 10.5% oxygen, 0.44% argon, and 0.06% carbon dioxide. Yeah, that's the composition of the air in the other half of the glass. So how do we think about this? So a fractional composition, you take the percent composition and divide by 100. So here in this gas mixture, 80% of it's helium, 20% of it is neon. So we've got 80% helium. Well, 80% is 80 parts per 100 parts. So 0.8. That's the fractional equivalent of 80%. It's 0.8. 20% neon, the fractional composition then is 0.2. So the pressure from helium gas, so we put P for pressure, subscript helium, to say this is the pressure due to helium, is equal to the fractional composition, 0.8, times the total pressure. It's 80% of the whole thing. Here, the whole thing is 1 atmosphere. If helium molecules are 80% of the molecules, the pressure from helium is 80% of the whole, or 0.1 times 1 atmosphere, 0.8 atmospheres. And the pressure for the neon is its fractional composition. It's percent divided by 100, 0.2 times the total pressure which is 0.2 atmospheres. And look, those add up to 1 atmosphere. Does that make sense? So a gas mixture contains 64% methane and 36% ethane. If the total pressure is 1.44 atmosphere, what are the partial pressures of each component? So the pressure due to methane will equal its fractional composition, the percent divided by 100. So 64% divided by 100, 0.64, no units, times the total pressure, 1.44 atmospheres. 0.64 times 1.44. 0.9216 atmospheres. And that should have two significant figures. The partial pressure of the ethane, you could actually calculate in two different ways. You could subtract this number from the total, because there's only two things in here, or you can do the calculation. So 0.36 from 36% times the total pressure. .5184. Oops. 2/6 atmospheres. If we add those together, what do we get? 1.44. So we should round these and say that 0.92 atmospheres for the methane and 0.52 atmospheres for the ethane. Any questions? Dalton's law of partial pressures. This says that the sum of all those partial pressures from each gas in a mixture equals the total pressure. So the total pressure is the pressure from gas A plus the pressure from gas B plus the pressure from gas C. However many different gases are in there, you add them all up and that equals the total pressure. A sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 745 torr, and the water vapor has a partial pressure of 24 torr. What's the partial pressure of the hydrogen gas? Well, let's think about what do we have here. We have hydrogen gas, and we have water vapor. Vapor is another word for gas. We have H2O in the gas state. So those are our two components. Dalton's law says that the total pressure of this mixture equals the pressure exerted by the hydrogen plus the pressure exerted by the water. Well, they told us what the total pressure was. P total is 745 torr. And this 24, that's the water vapor pressure. The partial pressure of the water equals 24 torr. This is a situation where actually rearranging the equation can be more complicated than just thinking about it. The total equals this plus that. If I know the total and I know one of these, how do I find the other one? Subtracting. The pressure from the hydrogen equals the total pressure minus the pressure of the water. So if you like equations, there's your equation. It's 745 torr minus 24 torr. And just like gases expand to fill their space, apparently my handwriting expands to fill the available space. 745 minus 24. 721 torr. Does it matter what unit the pressure's in here? Does it have to be in atmospheres? No. I just need to have them in the same unit so I can subtract, because you can't subtract atmospheres from torr or PSI from pascals or something. Any questions? Mm-hmm.
As far as like the water and the hydrogen,
Mm-hmm.
on our pre-lab it has different amounts. Do they change with like different amounts of hydrogen to water separation?
Yes. So what we kind of don't go into is that if you have a gas that is over the surface of water, the water evaporates and will put some of itself into the gas. And the amount of that, the partial pressure from the water, is dependent on the temperature only. So if the water is warmer, there'll be more water vapor. The vapor pressure of the water will be higher. If the temperature is colder, it'll be lower. And there's tables, you just go look it up, because people have done the experiments for us, and so we just go look it up. So yes, it can definitely change. Deep sea diving and partial pressures. Our lungs perform best at an oxygen partial pressure of 0.21 atmospheres, which happens to be the air at sea level, because, you know, this is where we live and our bodies work best here. If you get too little oxygen, so here's the 0.21. If you go to lower amounts of oxygen, you get into a state called hypoxia, low oxygen, and you're going to get lightheaded and have some issues, and then if it gets too low, you'll die. If you get too much oxygen, then you can end up with oxygen toxicity. So getting too much oxygen can always also kill you. So everything is toxic in some amount. We see this happening if you go to high elevations and you're very physically active up there, like at Grant Grove. You may get lightheaded, you might get tired more easily because there's not as much oxygen. The partial pressure of oxygen at that level is less because the total pressure of the air is less. And so there's just less oxygen available. Over about 1.4 atmospheres of oxygen, oxygen toxicity, twitching, tunnel vision, convulsions. This is not a big problem for people unless you're scuba diving, breathing pressurized air. Just breathing regular air, you can't get oxygen toxicity. But if you're breathing pressurized air, you can. Because you go down 30 meters below the surface of the water, the pressure of your air tank has to be 4 atmospheres in order for you to be able to expand your lungs and breathe. Well, at 4 atmospheres, the partial pressure of oxygen is 0.84 atmospheres. So this is higher than at the surface. And if you go to lower and lower depths, you're going to get a higher and higher partial pressure of oxygen. You get above 1.4 and you're going to have some problems. So what they do, well, take that back, go through the first part. Pressurized air, what's the main component of air? Nitrogen. So when you pressurize air, you've got nitrogen in there with the oxygen. You also get an increased partial pressure of nitrogen, and this can cause what's called nitrogen narcosis, or rapture of the deep. Apparently it feels a little bit to be like being drunk. Okay, you might think, well, maybe that's not so bad. Yeah, but if you're diving in the ocean, is it good to have impaired judgment? No, probably not. So to avoid these issues, deep sea divers going below 50 meters use specialized mixtures. They don't use just compressed air. They use things like heliox, which is a mixture of helium and oxygen. It doesn't have nitrogen in it. You don't need the nitrogen. You need the oxygen. So removing the nitrogen, they just replace it with helium, and that way you can breathe it at higher pressures without getting nitrogen narcosis. Okay, so let's do a problem here. A diver breathing heliox with an oxygen composition of 5% wants to adjust the total pressure so that the partial pressure of oxygen equals 0.21 atmospheres. What must the total pressure be? So this is using that relationship that the partial pressure of the component, the partial pressure equals the fractional component. It bothers me that your book doesn't give you a letter for that. The fractional component, or fractional composition, times the total pressure. Well, what's the fractional component of this mixture? The percent composition is 5%. How do we get that into a fraction? Divide by 100, so that's going to be 0.050. And the total pressure is what we want to find, and the partial pressure is 0.21 atmospheres. So the total pressure is going to equal the, I think I need a vacation. Divided by the fractional composition. So 0.21 atmospheres divided by 0.50. 0.21 divided by 0.05. 4.2. So meters, atmospheres. So the total pressure would need to be 4.2 atmospheres so that you can breathe this heliox and have an optimum oxygen level. What divers do is they'll have two tanks, one with heliox, one with compressed air, and as they descend, they'll switch the ratio and they'll gradually switch over to the heliox. Because one's great at the surface, the other's great really down deep, but you need in between in the middle. Any questions?
So when they're in the water, they calculate all of this? Or it's pre-calculated?
Well, that's why in order to go deep sea diving, you have to take classes and get certified, because you make some mistakes and you're going to kill yourself. And does it need to be calculated super carefully? Well, you need to have approximately the right amount. But when we look at this, we see that anywhere in this green area, you're going to be fine. You just need to know enough to avoid getting into the yellow and the red areas. But yeah, you do need to be aware as you descend, how deep am I, what am I supposed to be breathing of this or that, and switch it over. Personally, it doesn't appeal to me. I just like, being 50 meters under the water is just very claustrophobic, and I'll just watch videos of other people doing it. Collecting gases over water. So this is actually what we're going to do in lab today. We're going to generate hydrogen gas and collect it over water. And we've generated hydrogen gas before. We collected it in a test tube and then ignited it, right? And that was kind of fun, or scary, depending on your point of view. We're not going to use this exact setup, but it illustrates what happens. So here we have a chemical reaction that's releasing hydrogen gas. And the gas is trying to get out of here because it's building up pressure. And so it's going to go through this tube, and we're directing this tube into an inverted jar that was originally full of water. And as the bubbles come up here, they're going to displace the water. So they're going to cause the water to go down, but that traps the gas so it can't float away. So in this space, we have the gas, the hydrogen that we generated. We also have water vapor, because this water sitting here is evaporating. Water evaporates anything above, well, actually, even below freezing, it still evaporates somewhat. So there's water vapor in here, and there's hydrogen gas. Well, if we want to figure out what is the number of moles of hydrogen gas, how do we do that when there's a mixture? Well, the pressure of this water vapor, the partial pressure, depends on the temperature. The warmer it is, the more water there is. The colder it is, the less water there is in this gas mixture. And so we just look it up in a table like this. It's called the vapor pressure of water. That's the partial pressure of water at this given temperature. And so these calculations are actually really simple because all we have to do is subtract. So hydrogen gas was collected over water. Anytime you see over water, oh, we're going to have to look up the vapor pressure. At a total pressure of 758 millimeters of mercury and a temperature of 25 degrees Celsius, what's the partial pressure of the hydrogen gas? So we have a gas mixture. We have a total pressure. It's equal to the pressure of the hydrogen plus the pressure of the water. They're asking us, what's the partial pressure of hydrogen? The partial pressure of the hydrogen would be the total pressure minus the pressure of the water vapor. Okay with that? They told us what the total pressure was. Where do we get this pressure of the water? We look it up. It increases as the temperature increases. That's why they gave us the temperature. The temperature is not used in a calculation. The temperature is used so that we can look up the correct vapor pressure of the water. So the vapor pressure of water here is 23.8. So the total pressure was 758 millimeters of mercury. The partial pressure of water at this temperature is 23.8. So that means that the partial pressure of the hydrogen equals the difference. 758 minus 23.8. $758 minus 23.8. 734.2. But our initial pressure was to the nearest ones place, and so then our answer should be to the nearest ones place, 734 millimeters of mercury. Any questions? I understand it's a bit challenging. We should have finished this chapter yesterday, and so then you do the pre-lab after this. You had to do the pre-lab, or try to do the pre-lab without the lecture. So, but there's benefit in that too, because I think it makes you more interested in how do you do this, because I have this problem that I was trying to figure out, right? So, every cloud has a silver lining. Just sometimes they're hard to find.